Okay, concave, it has a few different meanings. I think, I don't know this for sure, but I think one of the first uses of concavity had to do with optics. If you have a lens, let's say this is a cross section of a like an eyeglass lens. This is a concave lens, as opposed to a lens that looks like this, a magnifying glass type lens, which would be called what? Anybody know? Convex, yeah. So we have concave and convex. Both of them are curving. It just kind of describes which way they curve, whether it curves in or curves out. We also talk about like concave and convex polygons. You guys remember those from geometry class a few years ago? So like a concave polygon would be a polygon. Technically, it would be a polygon where you could draw a line that goes in and out and back into the polygon. That would be the line test for concavity. But basically, it has a gap here. It's caved in at one point. So we've heard this term before. In calculus, concavity tells us which way a curve is curving. And things can either be concave up or concave down. So let's look at what this would look like. This is the definition of concavity. So the graph of a differentiable function y is concave up when y prime, or the derivative, is increasing. And it's called concave down when the derivative is decreasing. If you want, you can write this down. I don't think you're going to need to write this down. I think it's gonna grab pretty easily here in your minds. But let's look at what's happening here. So in this this graph I have on the left, this is just y equals x squared. The derivative here, I'm just going to draw some tangent lines. The derivative here is doing what? Okay, I heard some decreasing and I heard some increasing. One of those is correct. It is increasing. So I'm just kind of picking random numbers here, but let's say it goes from the slope goes from -4 to -3 to say -1 to 0 at the origin to +1 to +2 maybe somewhere. But the derivative is going up. So it's negative. And it's becoming less negative over here, and then it's positive and becoming more positive over here. So the derivative is increasing. So by the definition here that I gave you, if the derivative is increasing, then it's called what? Concave up. Now, just looking at the picture here, do you see why it's called concave up? One way you might want to think about it, especially in this case, it's kind of the shape of a bowl. And in this case, the bowl is facing up. So when the derivative is increasing, then that means that the curve is curving upward. Does that make sense? Okay. If the derivative is decreasing, like in the second one, and I'll just draw some tangent lines in here to show you what's going on. I think you can picture it though, probably. In this case, the derivative is doing what? It is decreasing. And since the derivative is decreasing, we would call it concave down. And if you picture a bowl, this would be like an upside down bowl. That would be concave down. All right. That means that the first derivative is decreasing. And looking to the left and to the right of the origin, we have a function that's increasing but concave down here. And we have a function that's decreasing and concave down here. All right, so basically the 4 different ways a function can look between critical points and between what's going to be called inflection points. We'll talk more about inflection points later. You could have a function that's decreasing and concave up. You could have a function that's increasing and concave up. You could have a function that's increasing and concave down, and a function that's decreasing and concave down. So those are the 4 different ways that a function can look between these critical values and the inflection points. And like I said, I'll talk to you about what inflection points mean in a minute. Does this make sense? Yeah? Okay. So how do we know then if the derivative is increasing or decreasing? What would be an easy way to tell if it's increasing or decreasing?
Second derivative?
Yeah, the second derivative. So if, and I'm going to write this down here because it's pretty important, if the second derivative is what?
Increasing.
Not if the second derivative is increasing. Is positive, yes. So if the second derivative is positive or greater than 0, that means that the first derivative is increasing. And then because of that, because the first derivative is increasing, we know what? Yeah, in fact, I'm going to skip this part right here and we'll just say it's concave up. If the first derivative, or I'm sorry, if the second derivative is negative, then the function itself is what? Now I added the y in there. Why do you think it's important that I put this in here? Could the second derivative be concave up or concave down? Yeah, it could. So I want to be clear here that I'm saying when the second derivative is positive, then the original function y is concave up. And when the second derivative is negative, then the original function y is concave down. And that's pretty simple, right? If I asked you to find intervals of concavity, whether it's concave up or concave down, what might be the first thing that we would do? If I asked you to figure out where is this function concave up and where is it concave down, what might you want to do first? Okay, find the second derivative. Critical points actually don't matter here. But we do want to find the second derivative, and then we want to determine when the second derivative is positive and negative, so what would we do next?
Find the zeros.
Yeah, figure out where the second derivative is either equal to 0 or undefined, because those are going to be the two places where the second derivative could change signs. Exactly. So we want to know when the second derivative is positive and negative, so we're going to start by figuring out where the second derivative could change from positive to negative. And then we can test the intervals just like we did with the first derivative. So when I ask if a function is concave up or concave down, we want to find the second derivative, and then we want to figure out when the second derivative can change signs and then test intervals. We're going to have points where the concavity is going to change. So on the left here, somebody described this here as concave up or concave down. Well, right here, what would it be? I heard an up and I heard a down. It is down. You see why, Vimmel? Okay, how about right here? Is it concave up or concave down? It is concave down. How about here? Concave up. So at some point here, it's changing from concave down to concave up. The point where a function changes from concave down to concave up is called a point of inflection, exactly. So it's concave down here, like an upside down bowl. It's concave up here, and what we would want to do to figure out where it changes is to set the second derivative equal to 0 and figure out where that's going to be equal to 0. Now, I want to show you what happens here. We've seen this before. At a point of inflection, and I'm going to kind of eyeball where the point of inflection is. That's definitely not it there. At a point of inflection, we're going to have a tangent line. And the tangent line has a special property that doesn't really happen anywhere else. Which is what? It goes through the function. Exactly. So normally at a tangent line, or at a point of tangency, the function kind of bounces, right? So normally we have a tangent line where the function stays on one side of the tangent line, like we have here. The function stays on one side. At a point of inflection, the function is going to be above the tangent line on one side, and it's going to be below the tangent line on the other side. Let me ask this about this function. How many points of inflection are there? So it starts out concave down over here, and it switches to concave up, so we ended up with a point of inflection somewhere in here. I don't know exactly where it is. We could figure that out if we knew the polynomial that represents this. But how many other points of inflection are we going to have? Two other ones? All right, so we're concave up here, and then at some point it switches to concave down here. You guys see that? So where it switches from concave up to concave down, we'll get a point of inflection. Then it switches back to concave up here, so we're going to get another point of inflection in there. So this function itself is going to have 3 points of inflection. It's pretty easy to do with polynomial functions, just like finding maximums and minimums were pretty easy with polynomials, where we find the first derivative and then set the first derivative equal to 0. It's the same thing here. We find the second derivative, set that equal to 0, and then we would test regions. So for this particular function, the second derivative here would be what? Positive or negative? Negative. How about here? Second derivative would be positive. The second derivative here would be, and here it would be positive. Does that make sense? Isn't this fun? All right, so that's concavity for you.